Hello all. This is going to be an exciting session where we will be talking on data indexing on the relational database. If you have seen an ELK video, how the way the Elasticsearch indexes the data, you would get to know how the recent day data indexing happens. The likes of Google and all other search engines, the way they do the indexing. If you haven't seen that video, please do watch it. The faster way of doing it. But then how does the relational databases, the old databases, right? Not the old databases, the databases like Oracle, SQL Server, Postgre, yeah, many of them. There's so many tons and tons of relational databases, right? How do they index the data? So first of all, why do we need an indexing? We all know that the indexing is required to faster access the data. So why do we really need indexing? Let us try to understand. So in the previous videos, you have seen how the data goes into the disks. Yeah. So let us assume there are two disks. Okay, and we have seen that the disks are segmented into sectors, and then there are tracks. Yeah, so if you want to, and then each of these areas are called blocks. Okay, and your actual data, what you insert into the database, this, if you see an example here, your employee ID 1 2 3 4 5 and name Ramesh, Suresh, Mahesh, Harish, Jagdish, Jagmesh, all of this actually goes and sits into something called data file, and that data file actually uh, resides here in each block. And each block in typically in Oracle, it is 8 KB. One block is of size 8 KB, and let us assume if this particular row is of 1 KB, then 1 2 3 4 5 6, they all can fit into this block. I mean, if you had some 100 rows, let us assume if you have 100 rows. Okay, so you have 100 rows, then you would actually require 100 kbs, isn't it? So 100 kbs actually cannot fit into an 8 kb block. So if you divide it, it is almost 10 12. Is it 12? Yeah. 8 tens are 80, and then 1696, right? Around 12. Okay, so you would need 12 blocks to store the data, right? And that blocks could be anywhere. So this is just one table, and your data is going into, let us assume there is one block here. Yeah, there's one block here, and the data goes here. So now the data is going into different blocks, right? It could as well go here. It depends on the availability of space, and it depends on the DBMS, right? How your database manager or your database engine, something like Oracle, where they are inserting the data, depending on the space availability, they manage the data. That is why they have built a product to manage all this data. And you want to search for something called a Sangmesh into this, right? So what happens is, now your data is segregated. It's like MDM, right? It's, in MDM the data is segregated into different systems, but here we are talking about a database server where it has a couple of disks, and your data is all segregated. So now how do you actually do a faster search? If you are searching for a Sangmesh, you would end up in doing a full scan. It will go and it will search all the blocks, and wherever it finds a Sangmesh, it would go and find it. Such a we call it as a full scan. It goes and does a full scan. So in the second part of this video, we shall see how this all happens. But then we'll try to understand it theoretically, and in the second part of the video, we'll try to see it with a live example. So that is a challenge. So that is why you need an indexing. So for example, what happens is, all these blocks, right? Where you're writing the data. So what happens is, there is something called, your Oracle or any other databases, they assign something called a row ID. Okay, so it is typically a 16-digit number, where it will have, it is generally represented in an hexadecimal way. I am not sure, but it actually has a block. It actually has the file address, and it is actually will have a row address. Okay, certain part, I think first eight digits are block, and then next six are and then this is I'm not sure. Yeah, so something like this. It is, you could see it for yourself how it is. So this is a row ID. So the row ID actually represents the physical address. So what do we mean by physical address? Where it is residing in the server. So this is a block address, right? And what is that file inside that block, and then the row. So this row ID actually tells you where it is actually residing inside the disk. So it could happen that that multiple, one block. Let us assume this is your block. Okay, 8 KB block, and this block may have the data from two tables also. It could happen, yeah. But then this will give you the right pointer, right? So row ID is unique and it will give you the right pointer. So that is the physical address. Yeah. So now when you are trying to index your data, we all know, right? Because the data is going and sitting in all the places. If you have seen the elk video, we told, right? So let us assume, if I have to give you an analogy, let us take a very common analogy of library, right? If you are a librarian, and then people, they dump a lot and lot of, just they will give you some 1 million books. Okay, and then they say you start a library, people will start coming and reading. So whenever people come and ask you to give a certain type of book, you wouldn't know, right, what is that book. So you need that indexing. So you will do that indexing. So you will either sort the books by alphabetically, yeah, or you will sort the book by genesis, or that department, right? Whether it is a science, a sociology, physiology, whatever, yeah. And then you will also try to give a certain number, like you have a row ID, right? You'll give a certain number. If you are stacking it, your library, these are your library racks, okay. And this is a person, if they could, you will direct them saying, okay, 1 to 1000 records are here. You would have marked them, okay. 1000 to 2000 records are here. 2000 to 3000 numbers are here. 3000 to 4000 are here. Or you will say A to B are here, C to do. It is up to the categorization how you would want to from your library, right? So this is the indexing. So typically, so you would have a row ID, that is your, and you saw your employee ID and name, these things, right? So you would want to do the indexing. So but then the real challenge is, if you had to do this indexing, what may happen is, let us assume you have 1 million data. Okay, so when you prepare an indexing, what is an indexing? It's just that for this unique ID, you would need some unique ID, right? It not necessary it has to be unique, but it is good if you have an unique content in your column, and it actually helps to do the indexing. So if you have given that record particular row, there is a uniqueness, and this record, you want this to give what, how will your index physical address, yeah, where it is residing, and this is your employee ID. So this becomes your index, right? For this one record, you'll give something like this hexadecimal. This is nothing but your row ID. So it is easy for, so whatever, whenever, if you were a database, you let us assume you are somebody who are designing a database server. What you would do is, for anybody to have a very good IO, right, input output, this is your input, right? For you to search, what you will do, first you'll come and see, okay, this table, employee table, employee name table, employee ID 1, you would have given a select star from your employee, yeah, where employee ID is equal to 1. So now employee ID 1, where it resides in your entire database server, you really don't know, right? If you not had an index, it will search the entire blocks, all the blocks in a database servers to get the data. However, if you have an index, what it will do is, your index actually also goes as in your memory. So it will also get into some blocks. Your index would also store. So your database, if you have designed your database server, what you will do, you'll first look into the index, or you'll see for this one, this is the physical address, and you actually reduce it. Yeah, so this is how it happens. But if your index itself is so big, right, so it does not really make sense, right? If you, one thing is, you'll have to store the index. If that index consumes the data, and if your index itself is so big, your index will also now get segregated. For example, your index cannot be stored in one block. So this is your index, okay, and this is your employee ID, and this is your physical address. Yeah. So if this itself is 1 million content, 1 million, then there will be so many things, right? So this itself cannot fit into one block. So now you need to break this also. So how logically you will try to break it? You could once again do some classification, right? So this, whatever this has gone into block 1, this has gone into block 2. So you will have another index. Okay, another index, a wrapper index. So where you will say the blocks, so B1, B2. So you will say then, so the 1 to 1000 have gone in here, 1000 to 2000, one have gone in here. So 1 to 1000, 1000 to 2000 have gone in here. So you can keep splitting this data, right, to make more and more indexes. So that way, it's if you see, it is forming a tree now. Yeah. So hence the way the database servers are designed is to have an indexing called a B tree. Okay, so most of the servers, they use something called B tree. B tree stands for balanced tree, and there's something also called bitmap, which we will see it in the next video, but we'll try to understand the B tree. For us to understand a B tree, let us first try to understand a binary tree. Okay, you might have already studied on the binary tree. It's very simple, right? So if you have a big number, let us assume I have something called 10, 20, 30, 40, 50, 60, 70, 80. Okay, so I have a big number of million. So if I have to search for 50, okay, in a database server, I will have to go from, this is called linear search. I'll see 10, 20, 30, 40, 50, then it comes in the fifth position. Okay, but then if I split them up, I will split them up something like, I will take the middle point, median, right? So my middle point is 40. Okay, so 40, anything less than 40 is what, 30. I will form 20. Yeah, I will form 10. Okay, 40, and anything greater than this thing is what, is 50. Yeah, this greater than 50 is 60, this is 70, this is 80. So the way we split it this, right? So what this binary tree will do, for a fee, for me to get this you would have got it at the fifth attempt if I had to search it linearly. Now what this happens is, it will search, come and first see here 40. Am I searching for a 40? No, I'm searching for a 50. So it will come and see, okay, for 50 is greater than 40, so you'll get it at a second attempt. So these are split in a very, very different way. So the way it happens is, you could very well split this further, something like, it will reorganize itself. So I will make this as a 20. 40, 20 is definitely less than 20, and I will make this as a 30. So you see here, this tree, actually I reduced it. Likewise, I could make 40. If I had decided, I could have made 80 here, the last node, right? 60, 70, and less than 80 is 70, or I could have made it as a 60 here. Okay, 70 is greater than this, 50 is less than this, and then I would have made the other three. So these are the trees I will show you. These are the self-balancing trees, which you'll get to know. It compares the data and it forms it. So likewise, but here in the binary tree, it is always one or two, right? You will have one and you'll have two childs, and then you'll have one node and you'll have a two chats. When you'll have, it's binary, right? It's like that. Yeah, but this will definitely solve the purpose, but then it does not. There is a more advanced way, something called B tree. Let me first show you the b binary visualization, and then we will go to the B tree. So here you have something. So let me add a number 1000. Okay, so 1000 I added, and let me add a number 9000. So 9000 is greater than this, so it got added it here, and let me add a number called 5000. So yeah, 5000 is less than that. Let me add a number 7000. 7000. So now you see this, it is shifting, and then let me add a number called 4000. So 4000 is less than 5000, so it will get added there. So let me add a number 10,000. No, 10,000 is not possible. I will add 999. It's 4-digit binary search. So it got here. So let me add something less than 1000. So it should get a below this thing. Let me add something less than 900. I will add something greater than 900. So this is how it is comparing and it is adding the data. So you see this is the binary tree. Yeah. So now let us try to get a little more advanced. Instead of, so in the B tree, what happens is you actually, it's the same concept. It's actually, if you go a little deeper, it is called M-way search. Yeah. M-way search. So the concept is very simple. Instead of one node, what you will do is, instead of having just one binary, what one key is what they say, we will end up having multiple keys. Okay. So what happens is, so this gives me a provision of having more. So there are three keys, right? So actually I will end up having more childs. These are 4 points, right? So they are called child pointers. I will have more childs. Okay. So there are three keys here, so I will have more child pointers. These are called child pointers. Okay. So it's just very simple. In the binary, the tree was big enough, right? So here with this, you can accommodate more and more keys. Okay. So here it will have this less than anything less than 10, right? So I will put it between 2 to 2, 7 and 9. So you could, once again, you could have three chats. Yeah, not necessary every time you have to have three nodes. Bare minimum, they would expect you to have two nodes. So but the concept is like this. I will show you a real example. So anything between 10 and 20, right? So you can have between line 11 and 9. So this will have between 20 to 30, and likewise it will have. So the idea is, where did we start? The idea is to store an index, right? In the index we had an idea, and for that idea we had to store the physical address, right? Row ID. So that is what we are trying. So if it is into 1 million, yeah, how do we actually break it? Keep breaking it. So the B tree will help you to break it. So let me show you this in an example. So B tree visualization window. Okay, so we will try to understand what is degree, but you get comfortable with how this is looked. So let me get a number 11. Okay, and then it started with one node, and then I will add 2000. Yeah, so it is getting added into one node now. Yeah, you see this? So it will keep changing because my degree is 3, means it will always take two nodes. So it did not take the third node, but you'll keep seeing it. See, we added three numbers, 2001. So it just took the intermediate number, right? Your 2000, there is one left child pointer, right child pointer, and now I will keep adding more and more numbers. You'll get to see. So 5000. So 5000, the 5000 went into another node, 5000 and 9000. Okay, so I will add another 2000. Yeah, so it now broke, and it came into it. One node is having two keys. So when we say max degree 3, it means it can have three childs. You see this, three childs and two keys. Okay, so now I will keep adding a lot of numbers. 6000. You keep observing the data. So it is forming many keys, different. You see this, it broke. Yeah, so and it split into the third level. Okay, so now 9000 is already added. So yeah, and 9876. Okay, we'll keep adding random numbers. So what we are trying to show is this is how the tree is formed, you know. It is making that tree. Yeah, and then if I have to delete something, I am gonna delete 2000. You see this? So I want to delete 2000. So your tree is self-balancing, right? It is self-balancing. And if I want to search something, 6000, I want to search something, so it will show you how it is going to search, right? So this is an advantage of how you can get to those keys faster. So this is how your Oracle maintains this data. When you have a big table and you write the index, you make an index. Typically it is B tree mostly, what it is taken, and this is how it self balances. You insert a data, okay, it self balances. Okay, you update a data, it self balances. If you delete a data, it self balances. And then when you query the data or search on the data, it uses that tree to get the data in a faster way. But please remember, when you define the strategy of indexes, should be in such a way. It should be, if it is on unique, then it is very very good. If it is on non-unique, it is okay, but then there are ways they do it. Yeah, so the idea of this session is to give you a feel. You will have to go into the deeper of this and try to understand. But then this always, you know, if you have a table with 5 rows, 5 columns, yeah, column 1 2 3 4, okay. So what happens is, if you set up the indexes on all of these columns, yeah, which is generally not a very good idea, because this, you may think that it will help you to get a faster data, hence you're writing the index. The first problem, if you try to create a lot of indexes, it is going to consume the space, because index also needs that space to be stored in the disk, right? Yeah, it space consumption will happen. So second thing is, when you are doing an insert, update, delete, then also it goes through that traversal, right? So through that index, at times it may find it, because while you are inserting the data, it has to readjust or rebalance. Yeah, so time goes into that, so that it causes, you know, your write operations will become slower if you set up a lot of. So there has to be a proper strategy that you are okay with the certain performance on the write, but you are going to gain a lot and lot of benefit in terms of querying. So it has to be that trade-off what you'll have to do to when you set your indexes. Okay, so, and this is very very important. Yeah, if you don't set your indexes, it leads to a lot of IOPS, right? A lot of power consumption, a lot of tables can happen. So typically how it happens is, why do you really have to worry is, you know, if you are a if you're writing a query. Yeah, so you let us assume you are setting a SQL editor here, SQL editor, SQL developer. You write a query, so this is on the disk. Yeah, this data is on the disk. So when this and then it, this is your server. Okay, this is your storage, and this is your RAM, this is your main memory, right? So it actually, whenever you query it, actually comes here, and then it it is queried and it gives this data onto the RAM, and then that comes and is displayed to you on the SQL developer. So when you are writing the queries, what happens is, you might have seen, either your websites, it takes a lot and lot of time to get the query, right? Or in the SQL developer also, if you are not querying it fast enough, you will see that you when you write a query, it takes a lot of time, and you'll see this, right, going on to see the data. So in the next part of the video, we will see how actually indexing helps, you know. So we'll try to see something like a plan on the query, where it tells you, Oracle actually tells you how the indexes actually help you to query faster. Hope this was useful, and do watch other videos to get more deeper insights onto how the database actually functions, and this would help you to actually design your procedures, queries, etc. And your program becomes efficient. Thanks for watching. Do watch next videos. Thank you. Bye bye.